Hello, welcome to our video lecture series on chapter 6.1. And on the last video, we hadn't quite finished this example. We're looking at a random sample of 500 moviegoers in 2013. 320 of them said they are more likely to wait and watch a new movie at home. So we were going through it to figure out what sample size we need in order to calculate a 90% confidence interval with a margin of error of 2%. And we're assuming the January 2013 proportion is still accurate. So here I recopied the information, and I'm using the sample size formula right here. And for 90%, that Z star is 1.64. We want the margin of error to be 0.02. And if we assume that the January sample is still accurate, we're going to use p hat of 0.64 and then 1 minus 0.64. Throw that in your calculator, we got 1549.21. But again, I'm going to throw in, we always need the sample size to be at least this big. So we need a sample size of at least and to be 1549.21, we're always going to move up to the next largest whole number, so 1550. So we need the sample size to be at least 1550. So don't forget, when we find the sample size, we're not doing regular rounding. We round this regularly to the nearest whole number, it would be 1449. We always need to go to the next whole number larger than this to get 1550. All right, I wanted to compare that with what if we go through the same exact process, everything here is the same, except what if we assume that January 2013 sample proportion is too dated? All right, it's been a number of years since 2013. Let's assume this 320 out of 500 is not a good sample anymore. Too much time has passed. So if we want to calculate a sample, or if we want to get a random sample in order to calculate a 90% confidence interval and be within a 2% margin of error. We have the same situation here, except the only thing that's going to be different in this formula, move up a little bit, is going to be p hat. So I go right here. I'm going to copy this and tweak this. So I'm using the same formula. So n needs to be at least z star over margin of error squared times p hat times 1 minus p hat. We're going to use a 1.64 because it's a 90% confidence. We want to be within a 2% margin of error, so 0.02. But now, if we don't know anything about the proportion, I'm going to throw p hat to be a 0.5 times 1 minus 0.5. And if I throw that in my calculator, 1.64 over 0.02 squared times 0.5 times 1 minus 2.5, I get exactly 1681. So we don't need to round up. I get a whole number in this situation. So we need a sample size of at least 1681 to be within a 2% margin of error for 90% confidence, and assuming we don't like this information anymore. So notice right here, that 0.5 is, I call it more conservative because it's going to get you a larger sample size given the same information. All right, last topic for chapter 6.1 is hypothesis testing. So hypothesis testing, we want the distribution of the sample proportions assuming the null hypothesis is true. So when we go to that standard error formula for doing a null hypothesis for a single proportion, we're going to set p equal to something, some proportion. So we're going to use that null proportion in our standard error formula. And the test for a single proportion, the standardized test statistic, Z, is going to be your statistic, your p hat minus the null, whatever you assume to be true, divided by standard error. And we could fill that in now for chapter 6, statistics p hat, the null, we're calling it p sub naught. And then that standard error is the square root of p. but we're going to use the null hypothesis times 1 minus p over n. And just like we talked about a couple videos previous, we need to make sure that n times the null hypothesis and n times 1 minus the null hypothesis are both at least 10. If they're both at least 10, then we could use the normal distribution and z-scores. Okay. All right, so of the 2,430 Major League Baseball games played in 2009, the home team won 54.9% of the games. We're going to consider 2009 as a representative sample of all Major League Baseball games. For 2009, this would be a population proportion, but for all Major League Baseball games going back 100 years and into the future, this will be our sample proportion. This is evidence of a home field advantage in Major League Baseball. All right, so I go right here, and I said before in class and in videos, you don't need to memorize these steps. I'll give these steps to you on assignments and kind of fill these out. So I want to go through the steps for this scenario, state the null alternative hypothesis using proper notation. I'm going to refer to this as we go through this example. Okay, so I've got the information copied here. If I write the hypothesis, h sub naught is p equals, and I want to think about, do we have evidence that home field advantage, that there is a home field advantage? So we're going to assume no home field advantage here. It's kind of a weird logic. And if there's no home field advantage, p should be 0.5. That's one game. We're going to assume equally likely option of the home team winning versus the away team. And h sub the alternative, we're going to assume p is greater than 0.5. All right, here's where I want to explain more what this notation means. So on here, my steps for hypothesis test, state the null alternative hypothesis using proper notation, but then I want to explain, what am I talking about with this null hypothesis? What does that p mean in a sentence or two? So right here, p is the proportion of games won by the home team in Major League Baseball. So connecting the hypothesis and my description, hope this makes a little bit more sense why we set the alternative to be greater than 0.5. P is the proportion of teams won by Major League Baseball teams. It should be greater than 50% if there's a home team advantage. And the sample says, yes, it is over 50%. The question is it over enough? Okay, determine the value of the observed sample statistic and the standardized test statistic. Okay, so the sample statistic is just given. That's your p hat is equal to 0.549. The standardized test statistic is z equals, let me go back here, the test statistic is right here. It's p hat minus the null over that standard error formula. So I'm going to fill in this formula. So it's 0.549 minus 0.5. And then for the square root function underneath, we're going to use the null hypothesis. So in here, I'm doing 0.5 times 1 minus 0.5 inside the square root, and then divided by, well, what's the sample size in this case? That's the 2430. 2430. And now if I throw this in my calculator, 0.549 minus 0.5, and then divide by the square root. 0.5 times 1 minus 0.5 over 2430. I get this to be 4.8309. Or we'll just approximate this to 4.83 as my standardized test statistic. So these formulas are a little bit messy, depending on the calculator you use at home or online. I'd encourage you to make sure you get the same number as I do, 4.83, rounded to two decimals. All right, so we've got the statistics, the sample stat, and the standardized test statistic. Confirm the requirements are met to use a normal distribution or a t-distribution. So I put this on here. We're going to come back to this, come to the t-distribution in 6.2. But for the normal distribution, we need to make sure that is NP greater than 10. And here, excuse me, our sample size is 2430, and P is 0.5. This is much bigger than 10. We get it to be 1215. So yes. And the other question is N times 1 minus P, at least 10. And this is also going to be yes. It's 2430. Is our sample size, and 1 minus 0.5 is still 0.5, so I get 1215. Yes, so we can use normal distribution. All right, so I've got at least 10 successes, at least 10 failures. Calculate P and make a decision. Okay, I'm going to go to stat key to get p-value. And since we are not given significance level, we are going to automatically let significance level equal 5%. So that'll be our go-to 5% significance level unless it's given. If we go to stat key, here's what I want to do. I want to take the standardized test statistic. I'm going to go to the normal distribution. And for, going back here, the alternative hypothesis is greater than, and my test statistic is 4.83. So this, the 4.83 is what I need to enter into my x-axis. So we're doing a right tail test. I'm going to change this entry down here to 4.83. Click OK. And we get something like this, the 6.8e minus 7. That number is 0.0000068. So it's not exactly 0. But we get in this scenario, p-value is approximately 0. So I'd say this is the statistical 0, not the absolute math 0. The p-value is essentially 0. So we reject the null hypothesis. And in this case, it actually wouldn't matter what significance level we chose. That's such a small p-value, a low p-value, we are going to reject the null hypothesis. All right, and then the last thing I want to do is write a concluding sentence. State whether we have enough convincing evidence for the alternative hypothesis or not, and then in context. So as I said in last class, when you describe the parameters and write your conclusion, I want anyone to be able to read that who has maybe not even taken statistics. I want them to get the gist of what we're doing. So this sample provides strong evidence that Major League Baseball teams do have a home field advantage and win more than half of their home games. So strong evidence that there is a home field advantage. Now I'd argue here this is not a huge home field advantage. They only won 5% more. But with such a large sample size and about 5% more greater than the null.